Hi everyone, this is Julian from Imperix, and this video is the second part of the introduction to our ACG software development kit. This video will be dedicated to the simulation of the buck converter and its control that we've put in place in the first part. So if you haven't seen the first part yet, you may want to watch it first. So we're going to start from where we left off. In this model and every other model that uses the ACG SDK, the simulation models both the physical quantities, such as the converter currents and voltages or the PWM signals applied to the switch, and the behavior of the controller itself. The whole idea is to be able to test the behavior of the controller in its environment in an offline simulation before switching to real power with a real converter prototype. To model everything accurately, a distinction is made between the physical quantities, the inputs and outputs of the plant model, which are modeled with continuous or semi-continuous signals, and on the other side the controller variables, which are discrete signals computed at each control period of the controller. So this reflects the sampling and the execution of the control algorithm within an interrupt routine executed at a fixed rate. So the model here will have different execution rates, the continuous signals and the digital signals. The interfaces between the two worlds are the library blocks, which represent the physical interface of the B-Box or B-Board controller. With the ACG SDK library, the execution rates are automatically defined in the whole model, according to the interrupt parameters in the configuration block, so you don't need to define them by hand. However, it is always good practice to check that everything has been interpreted correctly before running the simulation. To do so, Simulink can display color coding representing the different sample rates that it will use. So you can go to Display, Sample Time, Colors, and the legend appears. In this model here, we've got continuous signals in black and gray, and we've got discrete signals in red. The red sample time corresponds here to the execution rate of the main interrupt, previously set to 20 kHz or 50 microseconds, with an added phase shift to represent the default sampling phase of 0.5. If we look at the whole model, we can see that the physical signals are indeed continuous and the control algorithm is indeed discrete. The only issue here comes from the step block, which by default sets its sample time and thus the resulting computation to continuous. This is of course unwanted here, as the step represents a change in the one of the controller variables, and it should be refreshed at the interrupt rate. To fix that, we can simply set the sample time of this block to the predefined global variable control period, which can be used anywhere in the model and whose value is a vector with the sampling period and the sampling phase. If we update the diagram by pressing Ctrl D, Simulink updates the colors, and we can see that now the whole control algorithm has the proper discrete rate. A last thing before running the simulation, we will add several scopes to display the simulation results. And what we want to display here is the measured output voltage, along with its reference value to verify the reference tracking ability of our control, and the measured output current to illustrate the effect of the sampling phase. To be able to display the output current ripples, in addition to the sampled value, we will scope the current measurements directly at the output of the plant. So this is somewhat equivalent to connecting a current probe at the output of the converter and to display its measurement on an oscilloscope. Note here that I'm using two data type conversion blocks to make sure that the data types of the muxed signal match. If not used, this will lead to data type mismatch error. Finally, I will reduce the simulation time to 100 milliseconds to simulate only the time window that we're interested in. Now we can run the simulation by clicking the Run button. If we look at the output voltage in yellow, we can see that overall it follows the desired value in blue. The first two perturbations come from a step in the input voltage at 25 milliseconds and the load step at 50 milliseconds. We can see that the control is able to reject those perturbations. Of course, the control dynamics could merit further studies, but this would require another control strategy, and this is beyond the scope of this video. This graph also shows the behavior of the system under a reference step at 25 milliseconds, which the control is able to track. If we have a closer look at the measured voltage in steady state, we can notice that this is not exactly 12 volts. This is due to the plant output voltage, which is not perfectly flat due to the switching of the transistor, and even if those oscillations are limited by the output capacitor. So depending on when the measured value is sampled, this can lead to a slight steady state error. Next, we can watch the output current of the converter. On the bottom graph, you can see the output current ripples in blue, as if measured by a current probe, and the sampled value in yellow. The blue signal is sampled on the rising edges of the sampling clock displayed in the top scope. As expected with a sampling phase of 0.5 and a triangular carrier, the current ripple is always sampled at its middle, even during transients. This gives directly access to the average value of the ripples without any oversampling or extra computations. In short, with a sampling phase of 0.5 and a triangular carrier with a phase of 0, this ensures that the sampling never occurs at the same time as the duty cycle is updated, namely at the 0 of the carrier, and this produces PWM pulses that are always centered around the sampling instance. These kinds of concepts are modeled accurately by the simulation models of the ACG SDK library and can thus be verified in simulation. It is clear that if we now change the sampling phase to, for instance, 0.2, the sampling will not occur in the middle of the current ripple, and the sampled current will no longer represent the average of the current ripples. Similarly, if we switch to another carrier shape, the ripple will no longer be sampled in the middle. For instance, with a sawtooth carrier and a sampling phase of 0, the bottom of the ripple is sampled. Likewise, with an inverted sawtooth, the sampling will get the top of the ripple. Although this may be a nice feature of sawtooth carrier, this has the clear disadvantage that the sampling is always done exactly on the switching edges, which can cause severe perturbations on the measured value. In contrast, sampling with a phase of 0.5, namely in the middle of the switching period, this ensures that the sampling occurs far enough from the switching edges, and that at that time the induced perturbations are damped. To sum up, thanks to the simulation, we've been able to verify that our control algorithm works as expected, and we've been able to understand the effect of various parameters. In the next video, we are going to see how to generate code from the same Simulink model and how to execute it on a B-Box controller to control a converter prototype.